Hi, it's time for another math easy solution. Turn discuss further into applications of integrals and look at the area of a surface of revolution again, and this time look at the same example 3 that I went over in my last video, but now we're going to solve it using a different solution. We'll call it solution 2, and in this case we'll write x in terms of y like this over here. So make sure to watch my earlier video which I solved this example using the other way where we had y in terms of x. Now I'm just going to show that you could pretty much solve it the same way, but with this method. So this will make more sense to get through this example. So this states, the example states, find the area of the surface generated by rotating the curve y equals e to the x from x is 0 to x is 1 about the x-axis. So let's just draw this shape again. So if we draw the x-y axis to get a better idea, when x equals to 0, you have e to the 0. That's over, yeah, e to 0 is 1, so you get something like that. And then its exponential function goes something like that up to, all the way up to 1. So this is our curve y equals e to the x. And now the shape that we get basically we get it by rotating. So this surface generated by rotating this curve about the x-axis. So if we rotate about like this, we get a shape like this. If we rotate it about it, we'll get something like this. Draw this across all the way here. So it's not the scale, but you get the idea. So now we get a shape like this, drawn in 3D for the behind the scenes, and then we get something like this. And now this red surface around it, we'll call this S. And also now recall from my earlier videos on surface area formula. So surface area formula is basically equal to S is equal to the integral of and it's basically 2 pi y in this case, which is circumference, times by the arc length ds. So this is the circumference, and I'll show you how this is. So this is circumference, this is the arc length, and in this circumference, if you were to again take a small section across here, let's say we have a random section across here, we'll call this distance ds, that arc length, and then we rotate this about the axis, we get something that looks like this. So this is a very, very small section across, and now this surface area of this very, very small, if we consider this ds as infinitely small arc length, so we can consider that this section, the surface area is going to be, well, the radius is y across like this. So that's the radius, so the circumference is just 2 pi y, and then we multiply by ds, this thickness across, to get the full surface area, and then we use the integral to sum it up to infinity about the interval that we are looking for. And again, where ds, like I explained earlier, ds is equal to 1 plus dy over dx, the derivative in terms of x right here for y, dx. This was using solution 1, my last video. We wrote everything in terms of x. This is solution 1, and then in this video you could also write it, we're going to use to solve for this one, we'll call it solution 2. So if you rearrange this, you'll basically get 1 plus dx over dy squared dy. So this is what we'll use in this video, so I'll call this solution 2, and we'll basically solve this using this and write everything in terms of y. So this one's already in terms of y, so since we're doing in terms of y, the integral we're going to be taking is going to be, well, from here, well, yeah, it's going to be from this part right here. I'll just erase this. So it's going to be from this point, I'll draw this as a line like this. So it's from this point right here all the way to there like that. So this point here is at, well, at x equals to 0. So the intervals, let's go. At x equals to 0, we have y is equal to e to the 0, which equals to 1. and at x equals to 1, we have y equals e to the 1, which is just equals to e. So we're going to be taking this integral, the surface area, from 1 to e, and then ds, we're going to write it in terms of y. So to do that, we know that y equals to e to the x, so if we take the inverse, x is just equal to ln y, or where ln is the inverse of e to the x. So we have something like this, and again, you could view this in my earlier video on natural logs. So now when we take the derivative, so dx in terms of y, so dx over dy is going to be equal to the derivative of ln is just 1 over y. So we just switch the variable around. So we have this right there. So our ds now is equal to, well, it's 1 plus dx over dy, we're using solution 2. dy, this equals 2, plug that inside, 1 plus 1 over y is all squared dy. This equals 2, simplified further, we get 1 plus y squared dy. And now what we're going to do further here is basically multiply this top and bottom by y. So just so we have a common denominator of y squared and by y squared, so multiply by y squared and add them up, we get, this is going to be y squared plus 1 all over y squared. This is all square root. So we could simplify this even further. We get, in this case, let's move this around, it's going to be 1 plus y squared, and then this is going to be square root y squared dy. This just equals 2, 1 plus y squared over y dy, and that's our ds. So now we put this all together, we have integral up from 1 to e of 2 pi y ds is equal to, this equals, take the 2 pi out, so we get 2 pi, and then this is going to be integral from 1 to e of this y times it by ds, which is 1 plus y squared over y dy. The y's cancel, so we're just left with 2 pi 1e, and then this is going to be 1 plus y squared dy. And now this integral is the exact same as the one that we came up with in my last video, basically. So yeah, this is the exact same thing. So compare over here, compare with my last video on this with solution 1. So compare with solution 1. Alright, solution 1 video, where we ended up having s is equal to 2 pi. Instead of y, we just had u, but it's the same thing. So 1 plus u squared du. So it's the same thing, it's different variable. You can make this any variable you want, it's the same integral. So instead of reinventing the wheel, I'll just write the answer. So compare with this. So basically from my last video, so make sure to watch that, and how to derive, how to integrate this. And basically we get, the answer is going to be s is equal to, and it gets pretty intense, that's why I'm not going to redo it here. So it's going to be pi times e times it by 1 plus e squared plus ln of e plus square root 1 plus e squared, and then we had a subtracted by square root 2 minus ln of square root 2 plus 1. Yeah, and this is basically, I showed in my last video how to solve this, so I'll circle all this, and you plug this into the calculator, again like I showed in the last video, you get something like 22.94 roughly. So yeah, just make sure to watch how I derived this in my last video, which I used trig substitution, and also I used a previous video which I solved for a trigonometric integral. Anyways, that's all for today. If you learned from this video on how you could use in terms of y instead of dx. And in this case, it was actually slightly simpler because we didn't need to use substitution to get to this point. But in the last video, I used this substitution u to get to there. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another math easy solution.